Hola. Buenos días. Oh, brother. Hoy yo estoy muy cansado. ¿Ustedes están cansados? Un poco. A mí tampoco. No puedo pensar. Uh, okay, I'm going to start. I would love to chat in Spanish with you for this entire hour, but I better teach some science to you guys. So, good morning. We are done with gravitational fields. So, kind of going. Oh, I see a good sentence in the chat. Ya no puedo hacer nada. Mi mente ya se fui. Pero buenos días, muchachos. Okay, so I think that means I can't do anything already. My mind left me, but good morning, everybody. Okay, I think that's what that says. Okay, so we have just finished learning about gravitational fields. So this is the part of the course where we start kind of jumping from topic to topic. So we've basically just completed what I would call mechanics. So mechanics is just sort of your fundamental physics. So we've completed sort of the fundamentals of energy, momentum, kinematics. That stuff is kind of your fundamental topics, forces. And now we're going to kind of start going from area to area and doing some different things that are kind of at first glance unrelated. So in particular, we are going to start talking about error analysis. And this would make more sense in the classroom because we'd be doing, if we were in the classroom, we would be doing experiments, and experiments have uncertain data. And so we could use our own classroom experiments as an example, but we don't have that. So we're just going to kind of talk abstractly about error analysis for the next few days. There's a textbook. This textbook, Introduction to Error Analysis, the Study of Uncertainties in Physical Measurement by John R. Taylor. Excellent, 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 excellent book. Excellent book on error analysis, okay? I when I was in college, they taught us about error analysis, and it's like, this makes no sense. And then when I was in graduate school, in the lab, they had this book on the shelf, and I picked it up and I started reading, and I was like, holy crap, this makes a lot of sense. This book, they should just hand this book to undergraduate scientists and just say, just read this book and you'll understand afterwards. It made so much sense to me after reading this book. So, if you have any interest in statistics or error analysis or anything, I would highly, highly recommend this book. And I'm sure that I didn't read it when I was an undergraduate, but I'm positive that I could have even read it in high school and understood it. It's just a really clear textbook. If you know, I would say you probably need to know calculus, but if you know calculus, then it's really, really, really good textbook on error analysis. Cannot recommend it enough. Okay, so let's get started. So we're going to talk about analysis of uncertainties, okay? So let's say we're doing an experiment. ¿Cómo se dice experiment en español? I'm curious. So, yo debo aprender las palabras de ciencias. Experimento. Okay. Nosotros hacemos un experimento. So typically what you would do in an experiment is you would not just make the measurement once. You make the measurement multiple times. Okay? So you do an experiment. You repeat measurements. Okay? And you're not going to get the same answer every single time for various reasons. Okay? So, for example, when you so why wouldn't you get the same answer every time? You could have environmental factors that are changing. Okay, so the environmental factors are impacting the results. You could have your measurement tools are flawed; they don't work properly every time. You could think that you're setting up the experiment the same way every time, but you're not. There are even theories of physics, such as quantum mechanics, where, and in quantum mechanics, even if you completely understand the situation, when you repeat measurements, you won't always get the same answer every time. It's just the way nature works. Quantum mechanics works with randomness in it. So really what experimenters are doing is they're repeating their experiments and they're trying to zero in on what the actual number is that they're trying to find. Okay. All right. So I want to talk a little bit about accuracy versus precision. All right. And if you look up accuracy and precision, you're usually going to see like a dartboard, okay? And so maybe this is the true value. This dot is representing the true value. And you're making a bunch of measurements, okay? And each time you measure, you get a certain value. And maybe you get really close to the true value. Maybe you don't, okay? So you do a bunch of experiments, all right? Now, if we were to sort of look at the the average location of all of these x's, okay, the average location of all these x's is pretty close to the true value, okay? So we would say that this set of measurements is accurate. So an accurate set of measurements has an average that is close to the true value, whatever that means. Okay. Okay. So that's what accurate means. But notice that there is quite a significant spread in the experimental results. Okay. So we're getting numbers that are all over the place. Okay. But, all right, we're getting numbers that are all over the place. But when the day is said and done and we average all those together, we get something that's close to the true value. So this scatter in the data is called a random error. Okay, so you have some random error. You're trying to get the true value, but it's getting, your measurements are getting pushed around by random factors. Okay, so you have this random error. Okay, and sort of the size of this random error is called the uncertainty. So the uncertainty is a measure of how much randomness there is. Okay, so this would be a relatively high uncertainty because this region is fairly spread out. You know, something with less uncertainty would be, you know, if you have a bunch of results that are clustered close together. Okay. All right. So let's think about another experiment. A precise set of data is tightly clustered with low random error. Okay. So a precise data set might be something like this. See, all these measurements are clustered close together. All right, that's what a precise data set is. However, if we look at the average value of this cluster, it is not close to the true value. All right, so this is a data set that is precise, okay, but not accurate. All right, so accuracy has to do with the average. Accuracy has to do with the average measurement being close to the true value. Precision has to do with the repeatability of the experiment. Okay, you get something close to the same value every time you do it. Okay, so I'll just put repeatability. All right. So let's make some statements here. Precise data sets have low random error. Okay. Accurate data sets have an average close to the true value. Okay. So I can't believe I am really tired today because I basically just rewrote what I wrote right here. Okay, so you can have one or both of these properties, or neither, all right? So this would be a precise and accurate, okay? This is precise and accurate because the measurements are tightly clustered and their average is close to the true value. This data set is imprecise, but accurate. All right. So, you know, if you want to, what is more important, precision or accuracy? It kind of depends, right? I mean, accuracy, you know, what if you could only run your experiment one time or a small number of times? The less number of times you can run your experiment, the more important precision is. All right, because what if you could only run the experiment one time and your experiment is accurate, but you only get one shot at making the measurement? Well, in this case, what if you got that as your measurement? Then that's way off of the true value. So if you're taking lots and lots and lots of measurements, accuracy is really important because, precision is not as important because you are, you are able to average out all of the results, even if they're scattered all over the place, and get something that's close to the true value. If you have just one measurement to do, then you would hope that it's precise, and you would just kind of like cross your fingers. Oh, I hope it's accurate as well. Obviously, you want both of these. A really bad data set is one that has neither. So there are two types of errors in science. Okay, there's something called a random error, and a random error is different every time the experiment is rerun. Okay. It's different every time the experiment is rerun. So how can we combat random error? Well, what we do is so you combat this by running the experiment many times. Okay. And so what you do is you run the experiment many times, and then you just average the results. Okay. So once you average the results, the randomness goes away. All right. So that's an important term. The other type of error you can have in science is something called a systematic error. And systematic errors are much more devious, okay? Systematic errors are the same every time experiment is run. Okay? Now, the thing about a systematic error is it cannot be combated by rerunning the experiment. Okay? You cannot combat because it's the same every time. So the most likely cause of a systematic error is going to be some sort of flaw in your measurement apparatus, for example. So a great example of a systematic error is going to be something like a scale that is uncalibrated. Okay? So if you have a scale that's uncalibrated, you know how scales have that tare button where you set it to 0, okay? If you have an uncalibrated scale, every time you use it, it's going to be wrong. And it's going to be wrong by the same amount every time. So that's a systematic error. It's every time you do it, it's going to be wrong, okay? And it doesn't matter how many times you repeat your measurement. It's just always going to be wrong. So systematic errors are usually caused by measurement devices that are uncalibrated. And so systematic errors have to do more with experimental design. Okay? So you combat systematic errors with good design of the experiment. Okay? So I would call systematic, oh, here's a good SAT word. I'm about to use a good SAT word. Systematic errors are pernicious. Look it up, pernicious. They're devious because you could be doing an experiment. You're getting the same answer every time, okay? So you're like, gosh, this is a good experiment. Okay, I have so little random error. This is a great experiment. I designed it well, etc., etc. You might think you designed it well, but your design has some sort of a flaw that is introducing an error. So even though your experiment is very repeatable, it's very precise, okay, you have bad experimental design. So the number you're getting, you have confidence in your number because you're getting the same number every time, but your experiment isn't good. You don't have a good experiment, and so your number is meaningless. All right? So systematic errors are just pure evil because they can be there, but you don't know that they're there. You know random errors are there. They're the enemy you see because you're repeating your experiment, you're getting a different number every time. You're like, okay, I have random error. I know that. But you don't always know that you have systematic error. So notice how systematic error has to do with accuracy. Okay? An experiment that is accurate has no systematic error or a small systematic error. All right? Precision has to do with random errors. Okay? If you have a low amount of random errors, your experiment is precise. So these terms are related. Okay, so for this first page, we basically have discussed 4 vocabulary terms. We've discussed precision versus accuracy, and we've discussed random error versus systematic error. Okay? So now let's do a little math. So what I want to talk about is quoting a value. quoting an experimental result. Okay, so how do we quote an experimental result? Well, what we would do is we would say, let's suppose the experiment is trying to measure a quantity called x. So x is the quantity the experiment measured. Okay. So for example, it might be a time, it might be an acceleration, it might be an energy, something like that. And we say x equals 42, let's say, plus or minus, I'm going to say 42.15 plus or minus 0.09. Okay? So what does that mean? All right. This is our best guess at the true value. Okay. Which is typically obtained from some kind of an average of the results. Okay, so it's the mean value of all your experimental results. Okay. And then plus or minus this number, which is called the uncertainty. Okay. And so it defines sort of a window around your best guess that you're fairly certain that the result lies within that window. So it's plus or minus, okay? So if we add 0.09 to 42.15, we would get 42.24. If we subtract 0.09, we would get 42.06. So what this means is that I am fairly certain that the true value is somewhere within that range. Okay? It does not mean that the true value is definitely within that range. It means I think it is within that range with a certain probability. Okay? And I mean, the statistics of data analysis is really tricky. Read this book if you want to understand it better. But basically, I'm not going to go into the details of why, but there's about a 2/3 chance that it's somewhere in that range. Okay? And I'm not even going to tell you how do you calculate uncertainty. That's not the topic of this course. That's beyond the scope of this course. It has to do more with statistics. Okay? So there is a convention which this convention is not going to be followed in your quizzes simply because I cannot program it in. Okay? But this is the convention. The uncertainty typically has only one significant digit. Okay? So see how it has one significant digit, which is 9 in this case. So for example, it doesn't really, you generally speaking do not see an uncertainty of, for example, 0.09726. That would have 4 significant digits. Okay? So you just, you round it to one significant digit. okay? And then your best guess is rounded to that place value. Okay? So for example, the uncertainty, the significant digit is in the hundredths place. So that means that my best guess, I'm going to cross that out because that's a no-no. Your best guess should give all the digits to the hundredths place. Okay? So let me write down something that doesn't make sense. What if I said 42 plus or minus 0.09? Okay? Why doesn't this make sense? Because if my uncertainty is this small, why couldn't you give more digits in your best guess? Why not? All right? So do you understand what I'm saying? It's like if you're going to be that precise and have that low of an uncertainty, then your best guess better have those digits. All right? Similarly, what if I said, 42.695 plus or minus 4? This is another issue because you can see that my best guess is going to the thousandths place, but my uncertainty is in the ones place. So it's like, well, if you're that uncertain, why are you giving me all these extra digits? All right. So, so by following this convention, you have sort of a consistency that your best guess is quoted at the same level as your uncertainty. Okay. So that's a standard convention. Let's see if I can find it in this book. Look it right there. Oops. Come on. I'll show you in the Zoom room. But if this book follows that convention. Okay. So there are a couple of quantities, or a couple of ways of characterizing the uncertainty. Okay, so we're going to use this value, x equals, let's say, 7.2 plus or minus 0.4. Something like that. This makes sense, okay? Because my uncertainty is one digit, one significant digit. It's in the tenths place. And my best guess gives all the digits up until the tenths place, okay? So the absolute uncertainty is going to be equal, so absolute uncertainty in x is going to be equal to 0.4. Okay? The absolute uncertainty is going to be 0.4. But then there are other ways of characterizing that uncertainty. There's something called the fractional uncertainty, which is the absolute uncertainty divided by the best guess. So it's comparing the size of the two uncertainties. Okay, so maybe it's so that in this case it would be 0.4 divided by 7.2. All right. Which is 0.0555. And there's not really any rounding convention for stating your fractional uncertainty, so don't worry about that. And then there is something called the percent uncertainty okay, which is basically your fractional uncertainty times 100%. So in this case, it would be this times 100%. So that would be 5.5%. All right. So generally speaking, excuse me. Generally speaking, probably the fractional uncertainty and percent uncertainty are more important than the absolute uncertainty. Okay. Let me give you an example of a horrible measurement. Okay. Okay, let's compare. Let's think about this for a second. Is the measurement maybe I have a measurement that is 1,000 plus or minus 1. Okay. Maybe I have another measurement that is 0.5 plus or minus 0.7. All right. So these are two different experiments. All right. Just looking at these numbers, which was probably the better experiment? Okay. So you would say, some of you might be saying, well, this one has a larger absolute uncertainty. It's 1 versus this one is 0.7. Okay. So this one has a smaller uncertainty. It's a more precise experiment. So this one is better. But it's not really better because look at the percent uncertainty is more than 100%. So you have absolutely no clue where the value is. All right? Here, your percent uncertainty is 0.1%. Because 0.1% is 1,000. 1 out of 1,000. So this is a much more, precise experiment compared to what it is trying to measure. Okay? So I would say that this is the better experiment. That's the better data set. More convincing. I wouldn't be convinced at all by this data set. All right. So I got a couple more things to talk about. We got a 2-pager today. Bug, we got a 2-pager. Hazel, we got a 2-pager. Bug just barked. He just realized that I said something to him. I said we got a 2-pager. Okay. So now we're going to start to talk about, and we'll continue this next time. But what we are going to do is start talking about propagation of uncertainty. This is an incredibly important topic, okay? What happens in physics, for example, let's suppose that I was trying to calculate the acceleration due to gravity, okay? How would you calculate the acceleration due to gravity? Maybe you design an experiment and, you're dropping something and you let it fall and it has a certain height and it falls and it takes a certain amount of time to fall. All right. Takes a certain amount of time to fall. So you use the equation delta x equals 1/2 a t squared. All right. And And so then you can solve for the acceleration. The acceleration is 2 delta x over t squared. All right? So notice how when we measure acceleration, we're trying, the point of the experiment is to get the acceleration, but we're not measuring the acceleration directly. What we're doing is we're measuring a distance and a time, okay? And this distance and this time those are both uncertain measurements. So the uncertain measurements that we actually took during the experiment are used to calculate a quantity. And so as a result of that, the quantity that we're trying to calculate is also uncertain. So to propagate means to move forward, right? To, you can say like propagate the species means, the one generation is creating a new generation, okay? So propagation of uncertainties is when uncertainty in measurements carries over to uncertainty in quantities calculated from those measurements. Okay? All right. So that's called propagation of uncertainties, and it's really, 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 really important because extremely rarely are you directly measuring the thing that you're trying to get. Okay? Usually what you're doing is you're measuring something else. In particular, you might be measuring a distance or a time or a number of something, and you're using those quantities to calculate the thing that you're trying to get at. Okay? For example, when we calculated the charge of an electron, we didn't directly measure the charge of the electron. What we did, what Millikan did, it's a scientist named Millikan who found the charge of the electron, is he looked at oil droplets that were electrically charged. He basically put a static electric charge on an oil droplet. And then he put that, and the electric charge affected how quickly it moved back and forth. So and we don't have all the physics knowledge to understand the details of the experiment yet, but basically what he did is he measured the time it took for this droplet to go back and forth. And based on that time, he was able to deduce the charge. So that's an example where the uncertainty in the amount of time to go back and forth resulted in an uncertain value for the charge of the electron. Okay? So, what do we do? Well, let's say we had a quantity x. Let's say x is equal to, and let's say we have quantity x1 and we have a quantity x2. All right? So maybe x1 is 7.1 plus or minus 0.3. All right? And maybe the quantity x2 is 4.5 plus or minus 0.1. All right? So what if we had a quantity y that is called, and y is equal to 4 times x1. Okay? So because x1 is uncertain, y is uncertain. And this is really easy to do, okay? This is really easy to do because all you do is you multiply it through to both of them. So what I would get is if I multiply 7.1 by 4, I would get 28.4. And if I get 0.3 and I multiply it by 4, I get plus or minus 1.2. All right? So that's how that works. If you multiply something by a constant, then your best guess gets multiplied by that constant, and your uncertainty gets your absolute uncertainty gets multiplied by that constant. And so this is how you will do it in the quiz. But in reality, what you would do is you would then have to round this and follow the conventions of rounding. So this uncertainty has two significant digits, 1.2. So what you would do is you would then round that to one significant digit. So you have 28.4 plus or minus 1. But then this doesn't make sense because our, we have our best guess is in the tenths place, but then our uncertainty is in the ones place. So I have to then round my best guess to the ones place. So I would round it to 28. Okay. So if you were like writing a scientific paper or something, you would put it like this. But because I can't program the rounding into the formula questions, you would just quote it like this in the homework. But when you write your IA, you're going to do it like this. All right? What if I had a quantity z, which is equal to x2 minus, or let's say x1 minus x2. So we're subtracting two things. Okay. In this case, what we want to do, all right, is we would subtract the best guesses. So what's 7.1 minus 4.5 is what? 2.6. So we subtract the best guesses, 2.6. And then what we would do is we would, even though we subtracted them, if you add or if you subtract them, you always add the absolute uncertainties, okay? So this is going to be 2.6. So adding the absolute uncertainties, it's going to be plus or minus 0.4. Even though we subtracted them, we still add the absolute uncertainty. All right? So for example, if we had W equals x1 plus x2, I would add the best guesses and get, 11.6? And I would also add the uncertainty, so plus or minus 0.4. All right? So this is an example of propagation of uncertainties because I'm calculating something that is made up out of uncertain things. All right? And so, all right, so now let's do one that's a little bit more complicated. What if U was equal to 3x1 minus 2x2? All right. So what do we got to do? Well, first of all, we got to figure out we got to quote 3x1. So because it's multiplying by a constant, I multiply both of these by 3. So this is going to be 21.3 plus or minus 0.9. All right, that's this one. 2x2 is going to be 9.0 plus or minus 0.2. Okay, so now I am subtracting these two measurements. So what you want to do is you want to subtract the best guesses. So 21.3 minus 9.0 is going to be what? 12.3? Yeah, I think that's right. 12.3. And then I am Even though I'm subtracting, you always add the absolute uncertainties. Okay, so this becomes plus or minus 1.1. And then if this was your homework, you would just, and you're typing this in for your quiz, you would just leave it like this. But if you were writing an IA, you need to round this to one significant digit. So you would round this to 1. And then you would round this to the same place value as that. All right. So that's how it works. In the next lesson, we are going to learn how to do things like if you have x1 times x2. Okay. So propagation of uncertainties when things are multiplied together. All right, so that's my lesson for today. I will see you in the Zoom room.